For decades, the semiconductor industry followed a simple rule: shrink the transistor, get more computing power. But as we approach the physical size of individual atoms, that rule no longer applies. When you hear manufacturers talk about their new 2-nanometer chips, you might assume they've actually reduced the physical gate lengths down to 2 nanometers. They haven't. That measurement hasn't matched physical reality in years. Today, 2 nanometer is strictly a marketing label used to group together the next generation of architectural redesigns. The old architecture, known as FinFET, finally hit a wall. Once transistors get this small, the silicon channel becomes too thin to contain the electricity, and the current leaks out uncontrollably. To stop the leaking, the entire structure had to be rebuilt from the ground up. 3 manufacturers are attempting this transition for 2026: TSMC, Intel, and Samsung. Their engineering choices matter to anyone building hardware or investing in tech. Trillions of dollars in market capitalization and the timeline for training the next generation of AI models depend heavily on which of these foundries placed the right bet. The mandatory upgrade for all 3 foundries is Gate-All-Around, or GAA. By surrounding the silicon channel on all 4 sides, the gate regains tight control over current, shutting down leakage. The second, entirely optional upgrade is backside power delivery. This routes pure power directly from underneath. Foundries have to choose. Attempting both GAA and backside power at the same time clears up routing congestion and boosts power, but the manufacturing complexity is so high that entire wafers could fail on the line. The 2026 silicon war comes down to this specific choice. Success isn't about shrinking the smallest anymore. It is about balancing the extreme risk of these new architectures to actually get chips out the door. We start with TSMC. They hold the majority of the global foundry market and command a massive, proven manufacturing operation. For their 2-nanometer node, known as N2, TSMC chose the conservative route. They are adopting gate-all-around transistors, but they intentionally deferred backside power delivery to a future node. This chart shows 2026 projected yields, and TSMC's safe approach pays off. Their early manufacturing yields are hitting a highly profitable 70 to 80%. Without extra complexity, TSMC focused on shrinking SRAM cells and packing standard logic as tightly as physical rules allow. This extreme density gives designers the ability to cram massive amounts of cache memory into very small spaces, which is the exact profile required for mobile processors. Apple has recognized this reliability. They've already absorbed the vast majority of TSMC's early N2 capacity for their upcoming hardware cycles. The trade-off for this safety is raw frequency. Without backside power feeding the transistors, N2 offers less headroom for the massive power draws required by heavy AI accelerators. TSMC chose execution security and maximum transistor density over high-risk power delivery. For reliable yields and compact chips, they are the safest bet. Intel is in a very different position. Staring down a massive turnaround effort, they committed to delivering 5 process nodes in 4 years. For their 18A node, Intel is taking the leap TSMC avoided. They are rolling out their version of Gate-All-Around, RibbonFET, and their backside power system, PowerVia, at the exact same time. Stacking these 2 massive architectural shifts compounds the manufacturing difficulty. Consequently, 18A has lower overall density than TSMC, and initial yields are lagging behind, sitting between 65 and 75%. But PowerVia comes with a massive upside. Pulling the power delivery to the back of the wafer drastically reduces electrical resistance and voltage loss. This clean power delivery gives the transistors extreme stability under heavy loads, allowing them to hit higher clock frequencies at lower voltages. That specific profile makes 18A highly attractive for frequency-driven applications. It is custom-built for high-end PC processors and the extreme heat and power demands of AI data centers. Intel is trading away maximum density and safe yields for raw performance. It is the highest architectural risk in the industry, paired with a massive potential reward for high-performance computing. Samsung enters 2026 attempting to hold their ground with their SF2 process. Their engineering strategy is an iterative update. They were early to gate-all-around in their 3-nanometer chips, so SF2 evolves that existing tech while keeping backside power off the table for now. This graph illustrates yield maturity over time across the three foundries, and Samsung is struggling to scale. Their yields are hovering around 50%, alongside relatively modest performance gains over their previous generation. Because of these reliability metrics, outside designers are hesitant to commit their flagship designs. Samsung is relying heavily on aggressive pricing and internal volume from their own Exynos mobile chips to keep the lines running. Until they solve these manufacturing inconsistencies, SF2 serves mostly as a value-driven alternative rather than a primary ecosystem leader. Because of these diverging architectural choices, trying to crown an objective winner for 2026 misses the point. The question is, which engineering trade-off matches your hardware? This chart maps the three foundries based on target applications on the horizontal axis and risk and power profiles on the vertical axis. TSMC N2 sits squarely in the mobile and consumer tech sector. If your design is constrained by battery life and physical space, TSMC provides the unmatched density and yield maturity required to ship millions of consumer devices on time. Intel 18A occupies the high-performance computing and AI sector. If you are building data center accelerators that need maximum clock frequencies, Intel's backside power delivery provides the necessary electrical headroom, assuming you can tolerate the yield risk. Samsung SF2 sits lower on the yield axis, serving as a price-conscious placeholder for internal hardware while their process matures. The era of simply shrinking the transistor is over. The hardware that defines the next decade will be built by those who understand how to navigate these extreme architectural trade-offs.